Yes. So we would like to recall or recapitulate how do I do this? Like this. Free damped vibration before we damped vibration. Okay, we are actually already on forced vibration, but I would like just to repeat, okay, repeat part of free damped vibration. So first of all, we have mx double dot plus kx plus cx dot equals 0. So there is no load, and c is not 0. Then we introduce zeta, which equals c over 2m omega sub 0, or which is c2m k over m, and which equals therefore c2 square root km. So this is a value of zeta. And under these circumstances, x double dot, the equation plus, then we divide, that is omega sub 0 squared x plus, then c, okay? Then c equals 2 zeta m omega sub 0 x dot equals 0, but I divided by m, so this term is gone. Because I divided everything by m. Therefore, when I look for the solution x equals a in power st, I got the following characteristic equation. Which is s square plus 2 zeta omega sub 0 s plus omega sub 0 square equals 0. Therefore, this s12 equals minus zeta omega sub 0 plus minus zeta square omega sub 0 minus omega sub 0 squared. Or S12 equals minus zeta omega sub 0 plus minus omega sub 0 zeta squared minus 1. So we have then three cases. One overdamped. And that means zeta is greater than 1. So then we have S1 equals minus zeta omega sub 0 plus omega sub 0 zeta square minus 1. And S2 equals minus zeta omega sub 0 minus omega sub 0 zeta square minus 1. Okay? So therefore, solution will be x of t equals, yes, a1, and then will be exponent, and then first root from here, omega sub 0 zeta square minus 1, yes, t, plus a2 exponent minus omega sub 0 square root zeta square minus 1 t. And then we have this parenthesis, big parenthesis, and there is this one, in power minus zeta omega sub 0 t. Okay? So this is a solution for overdamped case. Now underdamped case. So that is page 2. Second, underdamped. Underdamped case will be like this. Zeta smaller than 1. So, because zeta is smaller than 1, therefore square root zeta square from minus 1 is, so this number is negative. So therefore it is good to write down it like minus 1 times positive number. So that will be minus 1 times 1 minus zeta square. So that is square root from minus 1 times square root 1 minus zeta squared. Or it is I times 1 minus zeta squared. Yes. So then solution will be x of t equals will be say b1 sine omega dt plus b2 cosine omega dt times e in power minus zeta omega sub 0 t, where omega d equals 1 minus zeta square times omega sub 0. So we did this algebra. We used Euler's formula in between. Now let us consider the case when it is critically damped. So zeta equals 1. Now if zeta equals 1, then S12 equals minus zeta omega sub 0 plus minus zeta squared omega sub 0 squared minus omega sub 0 squared. So first of all, this one is 1, and this is 1. So then this thing is 0. So S12 equals minus omega sub 0. So we have two coinciding roots. So the solution looks like this. Zeta equals 1. So S1 equals S2 equals minus omega sub 0. Then x of t equals a times, then we had the constant, times e in power minus omega sub 0 t. Look, please. This comes from this expression. Look. From this one. This is overdamped case. But if zeta equals 1, this is gone, this term. So exponent in power 0 is 1, so we get a1, but then there is minus zeta omega sub 0 t, zeta equals 1, minus omega sub 0 t. That is from this first one. But second solution does not come from here. Second solution, because we have coinciding roots, is t times the same as here, but another constant. So t times a2 e in power minus omega sub 0 t. This first comes from here. For example, if we have conditions x of 0 equals 0, then x of 0 equals how much? This is 1 and this is 0. So that just equals a1 and it must be 0. So we can see that if another condition is, please write it down here, we had x first derivative equals v sub 0. X dot at 0 equals v sub 0, initial velocity. I think time is not moving here. So initial, then we show that a2 equals v sub 0. And therefore x of t equals v sub 0 times t e in power minus omega 0 t. For example, if we solve analogous problem for underdamped case, I just wrote another set of constants. So underdamped case, the same problem, means initial velocity equals v sub 0. So x of t equals c1 cosine omega dt plus c2 sine omega dt e in power minus z omega 0 t. That is for underdamped case. So x sub 0 equals 0. Look, x sub 0, this is 1, this is 0. So therefore c1, x sub 0 equals 0, c1 is 0. So we are left then only with this term, c2. c2 sine omega dt e in power minus z omega sub 0. Maybe we don't need actually to write all of this, derivative. So you can write, if you want final expression, x of t equals v sub 0 omega d in power minus z omega 0 t sine omega dt. Okay? Where omega dt equals omega 0, 1 minus zeta squared, square root, 1 minus zeta squared. So that is for underdamped case. An underdamped case is a case that most frequently is encountered by us in life. Any questions? So damping anyways leads that yes, in the beginning velocity equals v sub 0, but displacement at time that goes to infinity goes to 0, diminishes. This is some local effect. It has effect in the beginning, but later it disappears because of damping. Damping takes care of so to say, this effect. So I dealt with these three damped vibrations because student asked me, one of our students asked today. So in response to his request, I decided to include this. Now, what topic? So that was recapitulation, I think, yes? We did start forced vibrations, is it not? Not yet. Okay, fine. So now we will start. What is the topic number? 13, okay. Forced vibrations. So we will deal with simplest possible case first. And simplest possible case will be forced undamped vibrations. So what we have is as follows: mx double dot plus kx equals, and say, imagine we have some number, say 5 times sine omega t. Okay? So what is omega? Omega is a frequency of excitation. So this is a loading. Okay, so what we have is actually a system, mk. So the loading input is load, 5 sine omega t. Output, I'm interested with x of t. That is output. So it is input. This is input, this is output. I'm interested with output. What will be coming out of this fact that sine omega t is acting on this system? Okay? And imagine we have x of 0 equals, how much do you want? First student.
Initial displacement.
Yes, how much?
Say
2. And x dot 0, that is not you, now someone else, please. How much do you want? 3. Okay, so these are the initial conditions. Now, because excitation is, say, sine omega t, so natural to look x of t equals look, please. X of t equals x complementary plus x particular. Yes? So xc is complementary solution, or solution of equation without loading. Yes? So mx double dot plus kx equals 0. We know how to solve this. We have here x of t equals c1 sine omega nt plus c2 cosine omega nt. Is it right? Omega n is natural, or just 0 if you want. And that is k over m. Yes, sir? Without loading. Without loading. Without loading means there is no this 5, etc. We just put that 0. So that is xc. So please add here this c's. That is complementary solution. And then we have x particular. So that particular solution means that any particular solution. That satisfies equation. So again, because it is a linear equation, x of t equals x complementary plus x particular. Now, complementary means that there is no loading, so we just discard loading for a moment. And we solve this equation. mxc double dot plus kc equals 0. Then xc equals c1 sine omega nt plus c2 cosine omega nt. Omega n is a natural frequency. Now we want to find particular solution, any particular solution. Okay? A particular solution, that means that we want to solve this problem. Mx particular double dot plus kx particular equals 5 sine omega t. Any solution of this. Okay, since on right hand side we have sine omega t, it makes sense to look for a particular solution proportional to sine omega t. Because look, I should get out of this whatever I will substitute sine omega t on the right hand side. So therefore I better x particular take, say, what is this, a times sine omega t. I don't know a. So let us differentiate. I substitute this here. I get m, a, capital A, second derivative, minus omega square sine omega t, plus k, a, sine omega t. This equals 5 sine omega t. So I can get a. A equals what? Look, please. 5, and here divided m minus m omega squared plus k. So that is a solution. So the solution is actually, look please, x of t equals x complementary plus x particular. Complementary was c1 sine omega nt plus c2 cosine omega nt plus 5 minus m omega square plus k. Okay, so that is what we have. So to find this C1 and C2, we need initial conditions. So x sub 0, for example, equals, someone said 2. X dot of some equals 3 you wanted. So we will do this. X sub 0, so at 0, this equals 0. So at 0, this is 1. So C2 plus 5 minus m omega square plus k equals 2. So from here, C sub 0, C2 equals 2 minus 5 minus m omega square plus k. That is C2. Yes, sir.
On the equation out there for x of t, should right below it, the final equation, should the 5, the particular solution,
Oh, yes. Yes, I forgot the sine omega t. So therefore, initial conditions, so let us impose initial conditions then. Yes, this will change. Five. X sub 0 equals 2. So when I substitute 0, then I see 2. This is 0, but this is 1. So therefore, I get C2. This equals 2. So C2 equals 2. And first derivative. X dot of t equals C1 omega n cosine omega n t minus C2 omega n sine omega n t, and then plus 5 omega cosine omega t divided by minus m omega squared plus k. Yes, also mistake?
If you go back to the general solutions, wouldn't that x of 0 also incorporate the second factor, which is 5 over?
You mean this? What is a general solution? General solution is this, everything. This one is a general solution. xc plus xp together.
Yeah, but I know this is like when you take x of 0, you then incorporate. Oh, I guess you have sine omega t, which is 0. I agree like that.
Yeah, I did. There it is. When I wrote t equals 0, this is gone and this is gone. So only this was left. Now I calculated the derivative, first derivative. Now first derivative at 0 will be C1 omega n, this is 1, this is 0, plus 5 omega minus m omega squared plus k. This equals 3. So C1 then equals 3 over omega n plus 5 omega over omega n minus m omega squared plus k. So I found C1 and C2. So I will rewrite this solution that I have. X of t equals C1. So I will denote this, look please, once I found it, I will denote it C1 with wave. So this is, I found, that is this. Times sine omega nt plus C2 wave cosine omega nt plus 5 sine omega t divided by m omega squared plus k. So that is a whole solution. Now I will rewrite this differently. Okay? We rewrite this. Now look, please, I will write down x of t equals C1 sine omega nt plus C2 cosine omega nt plus, look please, 5 sine omega t, and I will just take out m. Then we will have minus omega squared plus k over m. Let us concentrate on denominator only. So just 1, so that is m, minus omega squared plus, but this is k over m. What is this k over m?
Frequency.
That is frequency squared, natural frequency squared. So plus omega n squared. Now what happens, pay attention what happens here. When omega n, so what is this omega n? This is excitation frequency. This is natural frequency. So when excitation frequency is something that comes from outside. Natural frequency is something that is characteristic to the system, that is inside characteristic. These two can be very close, or maybe coincide. When omega equals omega n, then this denominator is 0, and the solution goes to infinity. Okay? So what we have actually is 6. So that is this figure. So that is omega divided by omega n. So when there is 1, then that is x of t. When omega equals 1, solution goes like this, to infinity. So this is called resonance. So resonance is when natural frequency or frequency of excitation equals to the natural frequency of the system. Resonance is when frequency of excitation equals to the natural frequency of the system. Yes, that is a question. Can you ask us the questions and I'll go to that? Yes, student is asking me to go, if it is possible, to a previous page. Oh, just he wants to rewrite this. So I thought that he wanted to ask me a question. Okay, so this is a resonance. So response of the system goes to infinity. You may want to write. Response of the system goes to infinity. Therefore, this condition should be avoided. We would like to avoid resonance. We do not want excitation frequency to equal natural frequency.
The end result of the which collapse that occurred in Minnesota 2 years ago.
Okay, student is asking whether that was a reason of ridge collapse in Minnesota about 2 years ago. My answer is I don't know because I did not read what has exactly happened. But certainly this resonance is not the reason of collapse of the Tacoma Narrows Bridge many years ago. So many people thought that it was this type of resonance. But it's not that. Okay. Therefore, so this resonance is the result of no damping in the system. If you remember, I started with undamped forced vibrations. I mean, when there is no damping, when this resonance occurs. Look, what I mean is when there, not just resonance, but solution going to infinity. Solution going to infinity is a result of no damping in the system. Resonance is equality of frequencies. If there is no damping, then resonance means infinite response. Okay, again, you may want to write down this. Resonance means equality of two frequencies, of these two frequencies. That is what resonance is. Resonance is equality of two frequencies. Frequency of excitation and natural frequency. Now, if we neglect damping in the system, then resonance is associated with infinite response. Yes. So the question is, what happens in a real system? That is our question. What happens in a system with damping? Because what we did here is we have a real system which has a damping, and we said, you know what, we are lazy, we don't want to consider it. We don't want damping. Okay? Somewhere, maybe on some planet, maybe there is some absence of damping, and maybe this is appropriate for that planet. But on this planet, this does not happen. So therefore, neglecting damping is an approximation or just analytical easiness. It leads to easy mathematics, so to say. Now this asymptote is at 1. At 1. But what happens in the damped case? That is our question. And that is what we are going to address now. What happens in the realistic damped case? So forced vibrations. So we have now new topic. What is our topic number? 14. Please write down forced damped vibrations. Not just forced as it is written here, but forced damped vibrations. So first of all, what we will deal with is harmonic excitation. Look, please, first write down mx double dot plus cx dot plus kx equals f of t. F of t is an excitation. F of t is an excitation. So we don't want to now, please write down, we don't want to deal with any general f of t. F of t general means any function. We cannot now, we are not able to now deal with any function f of t. In reality, we can have f of t any function. F of t can be, for example, linearly rising function in time. Look, linear, you may want to make linearly rising in time. Or f of t can be a rectangle over a very short period of time. That is a blast. or explosion. F of t can be like this. Okay, small time duration. We cannot now deal with those cases. We will deal later. Now we are able to deal with simplest possible case. Harmonic excitations. So again, before that I dealt also with harmonic excitation. If you remember, undamped vibrations. So I have P sub 0 cosine omega t. That is my excitation. P sub 0 cosine omega t. Omega is an excitation frequency. Or it is called also driving frequency. Driving frequency. Okay, now I would like to remember Euler's formula. Leonard Euler's formula. E in power I omega t equals cosine omega t plus I sine omega t. Therefore, instead of my original equation, P0 cosine omega t, I can actually write real part of that expression, exponent ei omega t, because real part of it will be cosine omega t. So that is what will be. Real part. So we have, why do I introduce this ei omega t? Because complex numbers will be very, very useful now. Therefore, I will do this. Or I will do one more step. One more step. This is real part of this. Okay, real part of this expression. Now I will say, I don't want this real part to be here. I would like to put this complex expression. But then I will not write x of t. X of t is a response to real part. So I will write, instead of x, y of t. Y of t will be response to the complex function. So I have to find y, and then from y I will take real part, I will get x of t. I do a trick, mathematical trick. So you have to write this down. First of all, I introduced, instead of P0 cosine omega t, real part of complex expression. Then I said, you know what, I don't want to deal with real part. I just leave the complex expression, remove the real part, because I would like to find a response to this function, which is easier. Later I will take real part of this, but then I will have to take real part of this also. So actually yes, sir? Can you ask again? I did not hear. Y, ky. Again, I'm repeating. I'm forgetting my x of t. I'm going now to another system. In another system, response is response to complex excitation. But there are no such a thing as complex excitation. There is only real excitation. So that is a mathematical trick. So therefore, I'm saying in my mind there is some function y, and this y is response to complex excitation. Once I will find it, then I will take real part of y, and that will be x. And that will be an excitation to real part of this complex excitation. Did you get the idea? So what I'm actually doing is I'm saying it will be easier for me to deal with complex numbers rather than to stay with real numbers. Complex numbers very often are very useful because they allow us to deal with square roots of -1 and other quantities. Okay, and then x of t will be real part of y of t. If you want, you can write down that I'm complexifying the problem to solve it easily. I want an easy solution, but in order to find easy solution, I must go into complex numbers. Please do not, please ask me a question. Please try to be with me, not go to anywhere else and think something else. Just be with me, bear with me. Okay, we go further if you have no questions. Okay, y of t, so that's a particular solution. Particular solution is like excitation usually. So I'm looking first for the particular solution. Because on the right-hand side there is ei omega t, therefore particular solution should be also in the same form. Small y of t equals capital Y times ei omega t. Now I find the derivative. First derivative will be I omega times capital Y, ei omega t, so it's small y. Okay? Then second derivative equals, of course, again I omega, so it will be minus omega square, and the function itself, so it's small y. Okay, so we substitute into this, so this particular solution satisfies this equation, particular solution. Yes, sir. Because capital, I have to multiply